All right, we are now recording. Let me tell you what I've gotten done and sort of a little bit of what I haven't gotten done. Okay. Friday and over the weekend, I was able to get your syllabus changed, updated, and loaded onto Blackboard under content. I put the research paper general instructions out there under Blackboard and under content. Put my locator card, I got that developed and put that on Blackboard under content. And I was able to upload all the chapter PowerPoint files for what these are worth. You know the quality of the PowerPoint in this book. I loaded all of those except chapter 14. If you'll notice, if you got your books yet, chapter 14 is...
That was not in the old book?
Yeah. What's that?
It was not in the old book?
No. It was there, but it's 8 sections, and they are fairly healthy sized sections. In fact, it covers a total of 82 pages. It's a big, long, hairy chapter. It would not have loaded in the Blackboard. I could not get it. I tried and tried. I was trying to find a way to split it into sections. I couldn't do that. It tried to load the whole thing and it would not go. I fought with it every time I've taught the course, and I've never managed to get it to upload. So, chapter 14, PowerPoints are not there. And that is, I think, one of the most important chapters, but you'll get the PowerPoints through Screencast-O-Matic, okay? So, I was able to get that done. And, let's see. I think I was at the right place. Yeah, okay. And then I was trying to get, the files that the recordings that I had made, I tried to load them on the Blackboard. They are too big, okay? They would not load on the Blackboard. So I checked with people who know, and they said load them into YouTube and then link YouTube to Blackboard. And that should work. So I can't remember if I started that on Thursday or not. But anyway, on Friday, I started trying to do that. All right, this has gotten to be so much fun. The Screencast-O-Matic, the free version, you can only record 15 minutes. Okay? So, but the schools provided this other version, so that's the one I'm using. So they say load it into YouTube. So I loaded it into YouTube and tried to load YouTube, and then they said, YouTube, you can only load 15 minutes. All right, what's the point here, okay? And then I talked with Dr. Monty, who's sort of one of the gurus on this, and he said that, yeah, you can load bigger files only if you've not created any problems with stuff before. You have to verify your account, verify that you haven't tried to upload copyright material and stuff. Well, obviously I hadn't. I just got started on it. So he said, but you have to have a cell phone to do it. Well, I don't have a cell phone. Okay, so I tried several ways around, and found out later, last night when I was doing this, or yesterday, when I was using my wife's cell phone for that. When I got to the point in doing it, it said, or you can do it this way. So you didn't have to have a cell phone, but they told me you did. So anyway, I started the process. So I got most of the, can't remember if I got this class done or not. I think I did. Of the files that I saved last time in Screencast-O-Matic onto YouTube. What I ran out of time and didn't have a chance to do was get those linked in the Blackboard. And I think that's a fairly simple step. So I'm looking to my computer whiz here to help me with that, to tell me whether that's a simple step. It seems like it ought to be, but I have not.
I'd probably just link it once and then make
What's that?
a playlist.
Yeah.
Okay, I've made playlists, and I've been loading into those, but I haven't made the link yet. So if I can make the link, then it'll be there. And it seems like that should be fairly simple, but I haven't had the time to try to do it, nor the opportunity to do that. So and I still have a few more to translate, like most of tomorrow's classes. I got today's classes into YouTube, but I don't know. I got Math 112 into YouTube. I didn't get linear algebra or differential equations into YouTube. So I've got to do that yet too. And then I recorded today's two classes and loaded those to YouTube rather than the other. And that seemed to go better. But I don't know how to when I was copying to that, I could tell it to put them in the playlist. Now I don't see a place to tell it to put it in the playlist, so I guess once it's in there, I'll put it in the play. Is that right? Yeah, we'll see. Okay. Anyway, most of your stuff's there. The videos aren't there yet, but hopefully, maybe even by the end of the day, they'll be there. We'll see. All right. Any questions on anything that we've done up till now? Okay. I've got all four of you here. So let's go. I think that we were on the bottom of page 583. Okay. And actually, I'm going to back up just a little bit. And this is what we're doing in example 8. Parametrizing a cycloid. And here's, I'll expand this, but if I go to write on it, it shrinks again, which is sort of a pain in the neck, but some of the body part. Okay, this is what a cycloid is. It basically traces the path of a point on a circle as that circle rolls down the x-axis, okay? And this is the place that does. Of course, this point will be back here at the bottom 2 pi later, so therefore the distance here is 2 pi if this is radius 1, which of course it is the way they've drawn it here. So that would be 2 pi later before that gets all the way around there, and then another 2 pi, and another 2 pi, and halfway in between it'll be at the very top when it's pi times r. So that's pi up, and this is a cycloid. Okay. Now, they parameterized it for us. We didn't have to, which is sort of a thank you very much, but here's how it parameterizes, okay? And, all right, the x is t minus sine t, okay? Now, the parameter here being t. T minus sine t. Now, I don't know if that makes a lot of sense to you, but let's pick those points we know. Of course, when t is equal to 0, this is 0, that's 0, sine of 0 is 0, so sure enough, that's at 0. And then when you get to 2 pi, you know when t is 2 pi, this will be 2 pi minus sine of 2 pi is 0, so that fits. So those 2 points fit. Let's do the one in between, at pi. Pi minus 1. Okay, pi is 3.14, so this should be 2.14, somewhere there. That should be how far? Is that right? When t is pi. That doesn't sound right. When t is pi, it seems like you should be, oh, of course you are, I'm sorry. Sine of pi is 0, okay? Sorry about that. Sine of pi is 0, so sure enough you are at pi. Pi minus 0 is pi, yeah. So the x is pi. So it seems like that part fits okay. Still didn't quite determine how we came up with that, but those points fit. Okay, how about the y? Okay, y is vertical distance here. When t is 0, cosine is 1. 1 minus 1 is 0. Sure enough, that was 0. Jump over to 2 pi, and cosine of 2 pi is 1. And 1 minus 1 is 0. Sure enough, it was at 0 there. And at pi, when t is pi, cosine is, second? No, it's 1 at 2 pi, so at pi, it should be minus 1, right? So,
2.
So this will be 2. 2, 1 minus a minus 1 is 2, and you go back here. I have to, oops, I went too far. Went too far. Wait, where is that? There it is. Okay, and sure enough, this is 1, 2. That at the top is 2. Sure enough, that looks right too. Okay, again, we didn't show how we got it, but we did show that at least those points make sense. Okay? All right. So that's the parameterization of your cycloid. Okay? Now, the argument in they do on the solution here. Let's just take a quick look at that. And by the way, this little side note may be of some interest to you. A stellar cast of mathematicians, including Galileo, Pascal, Newton, Leibniz, Huygens, and Bernoulli. Now, which one of Bernoulli's, I'm not sure, probably several of them. There was a whole family of Bernoulli's that were great mathematicians and scientists. Studied the cycloid and discovered many of its remarkable properties, and then you can go on and read some of the other things with that. But all those names represent people you could write on, and they also, you could write on what revelations or new things they found concerning cycloids. Okay. That would be another paper topic. Okay. So how did they go about getting these parametric equations? Okay. The point P, and that's at any point on that curve, the red curve for the cycloid, is located at the origin at t equals 0. As time t, the circle is rolled t radians along the x-axis, and the center of the circle then has the coordinates t1. Okay? So I guess let's go back to this and see if we can follow what they're talking about. Okay. Now, at t equals 0, it's at the origin. We already established that. As the circle has rolled, at time t, the circle has rolled t radians along the x-axis. Okay? Now that's in radians, and at some time t, and we already saw at t equal 2 pi, it was here, pi it was there. So sure enough, that is t, your x coordinate has to do with t, okay? Not only with t, but it has something to do with t, okay? So you're moving this way. Well, the center is moving exactly t. The center here is at 0. Right here it would be pi, 2 pi, you know, the center of the circle is moving exactly at the rate of t. Got it? Okay. T being the number of radians, but it also, you could actually count it as time too. You know, as it rolls, you know, and especially at a constant speed, it's going to be t. That's how far it goes, because the center moves very linearly along like that. Okay. Now, that's the center. So at any time t, your center would have moved t units along. Okay? So that's why they say the center of the circle then has coordinates t1. Okay? Now t is how far it's going on the x-axis. Of course, the center is always at 1. So the y doesn't change that. So anytime t, you know, or angle t, whatever you want to call it, the center is moved t units to the right, always at 1. Okay. Now, now they say, I love the way they say this. Oh, okay, sorry. Let's go to the next slide. 2 slides over. This is the one that perhaps is more helpful. This, to me, should have been followed almost immediately, that first slide. Okay? Now, the center has moved t units along here. Okay. Now, what has the x done? Okay? When the center is here, this point here, kind of hard to see. This one started here, and as this turn, this is going like this. So this point P that started right here has moved this way. So it's t minus, okay, what's the relationship between this distance and that angle t? Okay, now remember, arc length really doesn't have anything specifically to do with arc length, but as that is moved here, so what is this distance here related to that t? Remember, this is 1 here. What's that distance there? That's opposite of that angle t. So yeah, that would be sine t. Okay? Now, it moved t, the center moved t that way, but this is minus sine t. So the distance along the x would be t minus sine t. Okay? And sure enough, that's what we got here, t minus sine t. All right, let's see what the y is doing. It's such a pain in the neck to have to do this every time. Maybe I don't have to, but it just seems like it's... Okay. What is the y doing? Well, it started at 0. We saw that. Okay. And it's going upward. Okay. And it's moving up. This is 1. This is how far it is up. So it's 1 minus this distance here. What is that distance relative to this angle here? This is 1. That's cosine t. So 1 minus cosine t, that's how far it's moved up here. So that does appear to be where we get, and there's the illustration here. This is t minus sine t, 1 minus cosine t. That would be the y diagram. Okay? So that's where we get, let's see if I can bring that in a little bit better. The x is equal to t minus sine t, y is equal to 1 minus cosine t. So that's where we get those parameterized equations, parametric equations. All right. Let me get your name, please. Jonathan Rice, right. Oh, there you are, bottom of this page. Okay. Now we're up to 5. Okay? And all Y chromosomes, by the way. What have you done with the women, huh? You chased them off. Story of my life. Okay, never mind. Okay. All right, so that's really how we go about getting the parameterization of your cycloid. Okay. Now that we've gotten it here, let's extend that to a cycloid not just of radius 1, but of radius, the circle is of radius r. Okay? So how do things change here? Okay? That is unit circle that we just did. So if we take these equations, but now we have a radius of r. Okay? Now, yuck. Okay. Now, this is hard to describe without a picture, but I can't show the picture of this at the same time. This is where we get into our arc length. Okay? Remember, arc length, the equation for arc length is r theta. Okay, where r is the radius. Now before, r was 1. So in the theta, though, that's t in this problem. So RT would be how far the arc is, okay, minus then r sine t, just like we saw before. Before that was 1 times sine t. So it's r t minus r sine t, okay. And similarly before, that radius was 1, that's where that 1 came from before, so that's going to be r then. And then you're going back off from that r cosine t, that's the distance here, so that's going to be your y displacement. So basically, you put an r in every term, okay, of the x and the y, or the other way to write it, and I think this would have been a little simpler to write it this way, but there's probably reasons, of course, when I go to write, that shrinks it back down again. Pen, it's going to be red, so I want pen black. Okay. I would have been tempted to do x equal r times t minus sine t, y equal r times 1 minus sine, cosine t. I hate having to erase here because it's such a pain in the neck. So many. That didn't take. All right, that time it did. And then go back to that. Okay. All right. So basically, you just multiply r by your formulas you had for the unit circle. Okay. Now, okay. So you see these slides, not only are they pretty lousy slides, but they have them in such strange order too. If you're doing this with 1, then have that next to the one with 1, and then if you want to expound on that, have another one showing with radius r. But sure enough, that will work the same way. Okay? And if you made this radius r here rather than radius 1, then again, that construction would still make sense. Okay, I've probably done too much about that. It's a fairly complicated issue, but it's not impossible, but it just can be a little on the complicated side. Okay. Now, the next topic here in this section is tangent lines to parametric curves. Just as we use a tangent line to the graph, y is equal to f of x, how would we describe the tangent line of that? If that's a graph, some curve, y is equal to f of x, what would be the tangent to the curve? What would you deal with, huh? Derivative. Derivative gives you the what of the tangent line? Slope of the tangent line. Okay? So if you have a point, say, name a point. Okay? A little more generic. How about AB? Okay? Then the slope of that tangent line would be f prime of x. Right? And if you want the equation of the tangent line at the point AB, then the slope there is going to be f prime of A. That's going to be the slope. And then your point slope formula, anyone remember that? Y minus, which let's call it B, is equal to M times X minus A. Okay? But your M is this, so that your Y minus B is equal to F prime at A times X minus A. Okay? And then you can play with that and carry it, or move things around. So that's your slope of a tangent line at some point AB. That is your equation of the tangent line. And you can write it all in terms of Y is equal to B plus, well, let's see. Doesn't matter which. Maybe it would be better to do at least a little closer to slope-intercept form. Okay. F prime A, that's your slope, X minus A plus B. Okay. You don't have to write it either way, but yeah, that's a little bit clearer. Okay. Now, just as when we use tangent lines of the graph of y of x, f of x to determine the rate of change of the function f, we would like to be able to determine, by the way, some of you still don't have books. I don't like reading this much, but since you don't have books, I want to fill in the gaps here. To determine how y changes with x when the curve is described by parametric equations. Now, the slope of the tangent line is still dy dx, what we were calling f prime, but that's dy dx. That's still the slope, okay? But we have to use, to get our dy dx, you have to use the chain rule because both y and x are functions of your parameter t, okay? So, remember, let's do x equal f of t, and y is equal to g of t. Just shows they're two different functions. They don't have to be the same, obviously. Okay, then by the chain rule, dy dt is equal to what? This is sort of mixing our notation. G prime of t, right? Derivative of this equation, dy dt, would be g prime of t, right? And, of course, dx dt is f prime of t. Okay. Now, what do you get when you do dy dx? Okay. Now, that kind of looks like it would be, and indeed it is, g prime of t over f prime of t. Okay? So that's how you get your derivative. And that's still the slope of the tangent line, okay? But now it's a quotient of two different derivatives, okay? Now, they make a little statement here, and it's certainly very important. Of course, g of t and f of t have to be differentiable. If they're not, hang it up. I mean, how do you get a derivative of a function that's not differentiable? So those two have to be differentiable functions. And in general, I think you'll find that most of the time they are, at least when they're giving you the thing. So they're differentiable, and if that f prime of t, which shows up in the denominator, is continuous, not just f continuous, but f prime is continuous, and f prime is not equal to 0, it better not be, okay, continuous but not equal to 0, then, goodness gracious, glare is bad. The calculation is valid when f and g are both differentiable, f prime is continuous, and f prime not equal to 0. In that case, the inverse t is equal to f inverse of x exists, and the composite y is equal to g of f inverse is a differentiable function of x. Whoa, okay. Getting on into something pretty heavy there. But let's go to this theorem. What I think I'm going to do, just so it won't be quite as messy looking, is let me erase at least that line there. Okay. Now I'm going to zoom in. Okay. You'll have some of the rest of this in there, but sort of ignore that. The slope, now, this morning in my first class, or second class, the first one I did from this, every time I went to zoom in, it scooted the thing down. Now it's not. I haven't rebooted the computer or anything. It's just working better now. Why, I do not know. The slope of a tangent line. Now, remember what we had. C of t is sometimes called the path. We sometimes think of it as a curve, but technically it's not quite the same as a curve, but it maps the curve. But a little more precisely, it's the path that your object is taking at time t. X is a function of that time t, y is a function of time t. Now, it doesn't have to be time, I'll just say time, but it could be any other parameter other than time, but they're both got the same parameters. Where X of t and y of t are both differentiable. If they're not, you can't take the derivative of it, okay? Assume the x prime of t, then it's also, in addition, the x is differentiable, x prime is continuous, and x prime is not equal to 0. If that's the case, dy dx, which is the slope of that line, that path, is dy dt over dx dt, which is y prime of t divided by x prime of t. Now they went back to those functions rather than f and g. They sort of bounce all over the place with that, but that's exactly what you get. Y prime of t divided by x prime of t. Okay. Now, let's do example 9, and I think we have a figure for example 9. I'll blow it up now just for us to get a good look at it, but then, of course, as soon as I start to write, it will go back to that. So here's the function. C of t is, as indicated here, t squared plus 1, that's the x function, t cubed minus 4t is the y function. Okay? Now, what we're asked to do is A, find an equation of the tangent line at t is equal to 3. Equation of the tangent line at t is equal to 3. Okay? So what do we need to write down the equation of a tangent line? What did we need before? What did we need? Okay, we need points in the slope. Okay? and this is at t is equal to 3. An equation of the tangent line at t is equal to 3. So which you want to do first? Second? Which is the... Oh, okay. Okay, you want to start here, and you want to do c of 3. Is that what you're saying? Okay, c of 3. What would that be?
9 + 1.
Okay, 9 plus 1 is 10. Second? 27. 27 minus 12 is 15. 10, 15. There's the point that we're dealing with. When c is equal to 3, you're at the point 10, 15. So here's 10, and that looks like 15. There's t is equal to 3 right up there. Okay? So we got our point. What else do we need? You all told me before, second. Derivative. And what is the derivative? It's dy dx. And what did we just say that was? Dy dt over dx dt. All right, what is your dy dt? By the way, this is your y, this is your x, in case you were getting lost here. So what is dy dt is 3t squared minus 4. Very good. Okay? So this will be, my computer's going to sleep on me. It's laying down here. And what's your dx dt?
2t.
Is equal to what?
2t.
2t. Okay? And we want this where? At t is equal to 3. Right? So dy dt at t equal 3 would be 23. 27 minus 4 is 23. And dx dt at t is equal to 3 would be, is what? 6. Okay? So our slope then would be 23/6. Can't reduce that any. So what's the equation of our tangent line? Y minus 15 is equal to 23/6 times x minus, second, 10. Okay? Now, that is an equation of a tangent line. I'm not sure that's the one they're going to wind up with, but if you want to write it a little differently, you can multiply both sides by 6. That'd be 6 times y minus 15 is equal to 23 times x minus 10. And if you didn't like that too much, you could call it 6y minus, isn't that 90? Is that right? Is equal to 23x minus 230. Yay, what beautiful numbers we have. All right, if we wanted to subtract 6y from both sides, I'm not saying you had to, but you could, and maybe add 230 to both sides, that would give you, I'm going to reverse sides now, 20, ooh, I can't write. Yuck, I hate this. Okay. All right, if I can do it this time. 23x minus 6y is equal to, second, 140, is that what you said? Okay, 140. I thought it was what you said. Yes, okay. All right. That's another. That's probably the simplest looking equation. It's not really all that useful of an equation, but it is a simple looking equation. So that's your equation of the tangent line. You could have left it in slope-intercept form, which this isn't far off, but you still got a ways to go. That would be y is equal to 23/6x, and then you have to do minus 230 over 6 and subtract from that, or add to that 15. Yeah, so it gets a little messy, but you could do it in slope-intercept form. Probably much easier to graph it from that form, but you know, let's see what the book did. Lazy them, they left it in exactly this form right here. Okay, they didn't take it down to a simpler looking form. Perfectly fine. But it's sort of mystical where they want to leave it at any point in time. All right, so that's the A part. That's the equation of the tangent line at t is equal to 3. Now, number B says the points where the tangent line is horizontal. What's going to be true about a horizontal tangent line? What's going to be a max or a min? Okay. Okay. What else can you say about it? The derivative is 0, and that will be a max or a min usually. Okay, derivative is 0. Now, let's go back and say what our derivative was. This is at a given point. They told us that before, at t equal 3. Now we're looking for at what value of t are the points where the tangent is horizontal. Well, our derivative, if you go back and do it, the dy dx is equal to 3t squared minus 4 over 2t. Right? And we want to know where that's equal to 0. That's going to be where the tangent line is horizontal. Now, how is that equal to 0? That form right there is equal to 0. What does that tell you about that form? Does it matter what that denominator is?
Just can't be 0.
Not a whit. Yeah, it can't be 0, and the only place it is 0 is t is equal to 0. That will not give you a 0 slope. So we're fine with that. What will make that equal to 0? It's not the denominator. It's the numerator. Anytime that numerator is 0, it doesn't matter what the denominator is, as long as it's not 0, that's going to be it. So where is that numerator equal to 0? In other words, where is 3t squared minus 4 equals 0? Solve for t, yeah. So you would do t is equal to, but remember here, t could be plus or minus the square root of 4/3, which would be 2 over root 3, because the square root of 4 is 2, okay, plus or minus 2. All right, so those are the places where your first derivative is 0, therefore the slope is horizontal. And when that's the case, remember here is your negative t going towards 0. This would be here, so there's negative 2 over root 3. Here is where t is equal to plus 2 over root 3. Sure enough, those are your horizontal slopes, or the slope is 0. Okay. Now again, sometimes books write them as like 2 root 3 over 3. That would be fine. Here, they chose not to. It's perfectly fine. Plus or minus 2 root 3 over 3, or plus or minus 2 over root 3. Okay, I think we beat that one to death. haven't we? Oh, wait. The points where the tangent is horizontal. All we found out are the t-values where the tangent is horizontal. We haven't found the points yet, have we? We need, what do we need to get a point? Yes, the xy here, that curve there. So what we want to do is plug that value for t in there, and that would be, let's do c of, oh, I wrote it down. Yeah, there it is. Minus 2 over root 3. That would be what? What's your x value there? Okay, that would be 4 over 3 plus 1, that would be 7/3 then, wouldn't it? Okay. No. I'll get used to doing this one of these days. 7/3, okay, would be the x coordinate. What would be the y coordinate? Boy, what a pain in the neck wouldn't it be? Yeah, it's a -8 over 3 root 3 minus, that's the first part of it, so minus of minus would be plus 8 over root 3. Is that right? Okay. Well, to get least common denominator, you'd have to multiply this by 3 and that by 3. Okay. Those are time signs there. So this would be 7 root 3, 7/3. Boy, my writing gets worse and worse. Of course, this thing is so much fun to erase. Okay, 7/3, okay, and that would be 24 minus 8 would be 16 over 3 root 3. Okay, there's that one. And what would be c of 3 over, no, okay. Okay, I'm getting to be like Cameron in my writing, okay. Oh no, what's happening to me? Okay, that would be what? What's that? Oh, I see, okay. Well, guess what? When you square that, it comes out exactly the same as it did, and you're still adding 1 to it, so that's still a 7/3. All right, now let's see what your y value is. That would be 8 over 3 root 3 minus 8 over root 3. Exactly the same as the other, except the opposite sign. So that would then be 7/3 minus 16 over 3 root 3. Okay? Now, let's see if we're anywhere close here. Okay. I have trouble picturing what 3 root 3 is, and then dividing by it is really a mess. Let's see if it helps any to do 16 root 3 over 9. Okay? Root 3 is about 1.7. 16 ninths would be just short of 2, right? And multiply by something less than 2, and you're going to have something not far off from 4, plus or minus somewhere between 3 and 4, it looks like. So when the negative is in there, you're up here with a positive here, and when t is positive, you're there with the negative. And sure enough, and by the way, this is what did we say, 7/3. So that is 2 1/3. So just short of halfway. 2 1/2 would be right there, so 2 1/3 would be just short of that. So sure enough, there's the x value, same x values, y for the minus is plus, and y for the plus is minus. And something relatively close to 4. Maybe a little short of 4. What's that? Yeah, we did. And by the way, though, pay attention to the question. My temptation was find the value of t for which it's horizontal. That wasn't the question. Find the points where the tangent is horizontal. And then you have to plug in xy pairs. So we did have to do a little bit more work there. All right. Now, let's see what the next slide is.
That's going on for example 10.
Yeah. So I think before we get there, parametric curves, and by the way, there is another little side note here, which usually the side notes can be informative, expansive, maybe even instructive. These are called Bezier curves, is how I think you pronounce that. Were invented in the 1960s, fairly recent. Since I've been alive, maybe not you, but I've been alive then, by the French engineer Pierre Bezier, who lived basically, almost made it to the 21st century, but didn't quite, who worked for Renault Car Company. They still exist, don't they? Okay, all right. They are based on the properties of Bernstein polynomials, introduced 50 years earlier by Russian mathematician Sergei Bernstein to study the approximation of continuous functions by polynomials. Today, Bezier curves are used in standard graphics programs such as Adobe Illustrator, Corel Draw, and the instruction of computer fonts such as TrueType, PostScript fonts. Didn't know that stuff was started a little over 100 years ago. Okay, we probably wouldn't have had those fonts, those particular fonts, or the graphics capability of this. Someone else would have had to come up with it. They were behind it. Well, there you see at least two paper topics, Bezier and Bernstein, okay? But then too, how did they do their lives, or how did they come up with these things, you know, and applications of these? They gave you two. How are they applied in them? I mean, you could come up with bunches of paper topics just in that little blurb there. All right. So anyway, parametric curves are widely used in the field of computer graphics. A particularly important class of curves are Bezier curves, which we discussed briefly in the cubic case. Given 4 control points, okay, and why they give the equation, I think I know. Here's the situation. No. Goodness, this is hard to see. All right. All right, here are our 4 points. P0, P1, P2, and P3, in that order. Okay? Now, that is right. Yeah, that's right. Okay. They're just popping it on you to you here. The Bezier curve C is equal to x of t, y of t, defined for t between 0 and 1 by, now those are the curves, okay, without any other explanation except those where those 4 points are given. At least let's look at the left one first, okay. The right one, they give a different P1. Well, everything looks different there, okay. But P1, P2, no, P1, P0, P1, P2, P3. That's going to be different from 0, P1, P2, and P3 that way. All right, here are the equations, the parametric equations that make up these Bezier curves. I don't know, maybe this is way too much emphasis on it, but some of you may be interested in computer graphics. So, in case you are, here it is. All right. Here's your x of t based on 4 curves. Okay. A0 times 1 minus t cubed plus 3a1 t times 1 minus t squared plus 3a2 times t squared 1 minus t plus a3 t cubed. Okay, that's the x, and the y looks incredibly similar, except that, I mean, almost identical, except that you have different coefficients here. B0, B1, B2, and B3. Okay? But you see the coefficients 1, 3, 3, 1 are the same. The relationship to the parametric term, 1 minus t, and this is a cubic Bezier curve. 1 minus t cubed, t times 1 minus t squared times 1 minus t, and t cubed. Okay. Now, okay. They did say it earlier, but they didn't show it on the graphic. Okay. Your 3 points, 4 points that you're doing here is, what do they call them? What? No, they call them P. Okay, yuck. Okay. Okay. P0 is A0, B0. P1, A1, B1. P2 is the point A2, B2, and P3 is the point A3, B3. So basically, these are the values of the point. That's what comes into play here. For the x, use the x0 for P0, the x1 for P1, x2 for P2, and the x3 for P3. And then for y's, exactly the same thing, except we're using the y values for those points. That was your B0, your B1, B2, B3. Okay. Now, let me just say a couple things about this before we go on. Again, I feel like we're harping on something that you really don't use that much, but I want you to recognize a few things. First, the coefficients 1, 3, 3, 1. Anyone know where they came from? Have you heard of the binomial expansion? Those are the coefficients for that. For a number, it's just 1, okay? X to the 0 is 1. For x plus y, the coefficients are 1 and 1. For x plus 1 squared, okay, that was x plus 1 to the 0th power. x plus 1 to the first power. X plus 1 squared would be x squared plus 2 xy plus y squared. So your coefficients are 1, 2, 1. And then for the cube, when you're cubing a binomial, your coefficients are 1, 3, 3, 1. And anyone want to hazard a guess what for the fourth power? 1, 4, 6, 4, 1. Pascal's triangle. That's exactly what you're using there. And you can just keep expanding those forever. Now, you've got the coefficients that are in there that can really throw things off. But the other thing to notice when you're expanding, the 1 minus t, notice its power is 3, 2, 1, 0. And going the other way, the t's are 0, 1, 2, 3. So one's decreasing, one's increasing. Very typical of, if you ever do any statistics, you'll see the same thing is going on with P's and Q's. When we're not going to get into what they are doing, but that gives you probabilities. Okay, so it's the same type of a deal that you see all over mathematics is that thing. So that's how we get the Bézier curves. Now, if you rearrange the order of the points, of course that's changing your coefficients, you can get very different looking curves. Okay, and that's where I guess we go back to this. Did that again. All right. If the points are basically following a pattern like that, your Bézier curve is going to follow a pattern a lot like that. But if your points are up here, down here, up there, down there, you know, then you're going to get some waviness in the curve. Okay? But these kind of curves enable you to then do some pretty reasonable things graphically. Everything's smooth curves. It's nothing adjointed, you know, polynomial, you know, just, or what you call that, into, can't think of the word, they use it in weather, polygon, yeah, polygon, nth degree polygon. Okay, so, let's see. I think example 10 is going to be an example of this. And let's see. Obviously, the previous book edition thought to draw the hand sketch made in 1964 by Pierre Bézier for the French automobile manufacturer Renault. He used it to design the cars, you know, make them more aerodynamic and that type of thing. They didn't have computer graphics there. He was doing them by hand or pretty close to it. Okay, so we're not going to do that. But let's see what example 10 will show. Show that the Bézier curve is tangent to the segment P0, P1 at P0. Interesting. Okay. Whatever those are. Okay. All right. So here's what, in fact, let's go, well, let's just do it here. X of t is equal to thing A0 1 minus t cubed plus A1 1 minus t squared t plus A2 1 minus t squared plus A3 1 minus No. Yuck. I'm trying to do this without erasing, but sometimes it just is too nasty. Okay. All right. T cubed. Okay. Y of t is equal to b0, 1 minus t cubed, 1 minus t cubed, plus b1, 1 minus t squared, t plus b3, b2, 1 minus t, t squared, plus b3, t cubed. Okay. Now, all right. So one thing we've got to do here is find out what your tangent line is here. It says, show that this is tangent to the segment there. Okay. Well, let's start with the segment. Remember the segment from P0 to P1. P0, P1. That segment. Okay? What is the slope of that segment? What's the slope of that segment? Here's your P1, there's your P0. Pretty straightforward, isn't it? Here's your P0, there's your P1. What's the slope of the line that goes between those 2 points? Remember your old slope formula? B1 minus B0 over A1 minus A0. Okay, that's the slope there. All right, now let's see what your slope is of these two parametric equations. In other words, your dy dx, which is basically going to be dy dt over dx dt. Okay, what's your dy dt? Okay.
Where did you get the initial equations from?
What's that?
So where did you get those two initial equations from?
I can't hear you.
Where did you get the two initial equations from?
Oh, those are the Bezier curves. You're on in your book on page 585, equations 9 and 10.
You just left off the threes.
Well, that's the derivative.
Okay, that's the derivative with threes.
I'm sorry? Did I leave off a term? Oh, I left off my threes. Oh, yeah, threes here, 3 here, 3 here. I'm sorry. Yeah, I forgot my coefficients. Yeah, got it. Thank you.
You're welcome.
Okay. Yeah. Okay. Now, what we're doing this, remember, we're doing it at the tangent at P0. So that's the only curve we need. We don't need the P1's curve point, the derivative there. We're not going there. We're interested at P0. That's what it says here. Show that Bezier curve is tangent to the segment at P1, at P0. Okay, so we just need dy dt there. So what is dy dt at P0? And that's exactly what this is. This is at P0. Okay? Take the derivative of that first one. Second,
X of t?
I can't hear you.
The
With
X
res-
of t at the very top? Is that what we're taking the derivative of?
I was going to do the y first because that's on top. So this one right here, take it with respect to t. 3 times, I'm going to put the b0 in there too. 3b0 times 1 minus t squared, chain rule times a minus 1, right? Okay, plus, I think we'll lose that plus in a minute. Okay.
Or no, that's a different.
Yeah.
Is that one?
I'm sorry?
Would that be 6b?
Yeah. Yeah, it's going to be 6b1 times 1 minus t times t. You got a product rule here, right? Okay. And you got another plus, oh yeah, and then you got a minus. Ooh, I hate this. I'm just going to have to look ahead and do, I was trying not to do that to you. Okay. Because chain rule there, we had another minus sign in there. Okay, so that was when we did this one times that, derivative of this times that, plus this times derivative of that is just going to be 1. So that's just going to be a plus 3b1, 1 minus t squared, right? Okay. Of this next term, and it doesn't matter how you break up the product, let's do that one times that, right? Derivative of that is basically going to be a minus 3b2 times t squared plus 3b2 1 minus t times 2t, so that's going to be 6t. I'm using the Cameron rule. Just right over it, okay? Let's see if I can clean that up a little bit. Yeah, that looks a little better, okay? All right. And then the last term is going to be, I know it's going to be a minus, okay, because you're going to have a minus 2, so that would be 6. No, I'm sorry, it's not 1. It's going to be a plus. 3b3. Sorry about that. Goodness, this thing is such a pain to do. Yeah. Okay. That's going to be a plus. I'm losing my place. There it is. 3b3 t squared. All right. Oh, man. That was the dy dt. Let's do the dx dt. Okay, it's going to be just like it, except it's going to have a's in there. So that's going to be, if I can find it, minus 3a0, 1 minus t squared, minus 6a1 times 1 minus t, plus 3a1, 1 minus t squared, minus 3a2, t squared, plus 6a2 1 minus t plus 3ba 3t squared. I think that's got it. Okay. Now, if you divide those one by the other, and we're doing this at t equals 0, because remember that is where at p0, that's when t is equal to 0. So now we can plug that in at t equals 0, and our dy dt at t equals 0 is going to simplify pretty dramatically, I think, minus 3b0 times 1, right? And then this is going to be 0 plus 3b1, okay? Okay. This one will be 0, that one will be 0, and that one will be 0. Okay? Your dx dt at t equals 0 is going to be, here we go, negative 3a0, done. This one will be 0, plus 3a1, done. That one will be 0. Did I leave off a term before? Yeah, I think I need a t here. Yeah, I left off that t. So that one's going to be 0, and that one's going to be 0. So then the ratio here, dy dt, or dy dx, is the ratio of those, is minus, okay, let's pull out the 3 and have b1 minus b0 over 3 times a1 minus a0. The 3's go out, and guess what we're left with? Exactly the same slope. Right? That's the slope we got just looking at the 2 points, and here's the slope we got by taking the derivatives. Of course, it helped a lot that we're doing at t equals 0 right there. But at t equal 1, we would have been here, and those terms would have, 1 minus t would have gone away. And yeah, so there would have been some helpful things at several of the places, but not at all. Okay. Whew. All right. Now, things that we did with regular curves, taking slopes, finding tangent lines. We just did them with these. Okay? Other things we did with regular curves, areas under those curves. Well, can we do an area under a parametric curve? Okay? And that's where, whoops, that's not the one I want. Not Renault. Ha. They don't have the slide in this. Okay. All right. Now, I think this is where I go to a white screen. This is area under a parametric curve. They don't have this on the slide set, so I'm going to have to do it myself here. As we know, the area under a curve is given by a curve given by y is equal to h of x. Okay? When h is always greater than 0, greater than or equal to, or they include equal to 0, for a less than or equal to x is less than or equal to b, somewhere between a and b. And that area under the curve a is equal to the integral from a to b of h of t, although they put an x. Okay, doesn't matter what your dummy variable is, but dx. Okay, that's what your area is. All right. Now, when the curve y is equal to h of x is traced once by a parametric curve, and this curve now is going to be c of t, and that's going to be the point x of t, y of t. It's your parametric curve. Okay? And it says as in the figure, and we don't have the figure, so let me just draw a gross representation of, okay, there's your curve, and this will be x of t0, and this will be x at t1. This obviously is y at t0, and this value here would be y at t1. You don't have to have that there, it's not important in this case, but that's, and this is your c of t. All right. Now, this is your a, that's your b. No. Yeah. Okay. All right. Now, here's the area we used before. Here's the area we're going to use now. A is equal to, now, remember this was x at t1, A, x at t2 is B. So here we're going from t0 to t1. So our d is going to be dt here. All right. Now, this is the y-axis, this is the x-axis. Okay. The function h of x is basically being replaced by y of t. Okay. And your dx here, all right, get this sleight of hand here. If x is this, dx is equal to x prime of t dt. All right? So instead of dx, we put x prime of t, and we already had our dt there. So that's how you do the area under here. Your h of x, which was your y function of x, that's the same as y of t here. Okay? And your dx, because x is equal to x of t, dx dt is going to be x prime of t dt. Okay, so that's just your simplified area formula. Basically, almost exactly like we had before. Now, example 11 says, find the area inside the ellipse in example 5. Inside the ellipse in example 5. Example 5 was back on, goodness gracious, where is it? There it is. Bottom of page 581, The picture is actually on page 582. Okay? It looks like that's example 6, but it's not. Okay? So, we want the area inside the ellipse. Okay. So I'm going, well, let's see. That ellipse is probably on the slide set. Let's go back and, so I don't have to redraw it. It's going to take me longer. There it is. There it is. I think that's your ellipse. All right. And there's the parametric equations for it. Okay? I think that's the one they're talking about here. Okay. Now, if we're wanting the area inside that ellipse, here is the deal. Now, here is t is equal to 0, and you go counterclockwise around here till you get t is equal to pi. If we can find the area under that curve and double it, that will be the area inside the ellipse. Does everybody buy that? Okay? So what that area inside the curve there would then be, from what we just did, the integral from t equals 0 to t equal pi. It's going to be twice this because we're going to double it. Okay? And our parametric equations then was, here is the y, so that's going to be 2 sine t, and then your dx, let's do dx, is equal to what? If x is equal to 4 cosine t, what is your dx? 4, I think it's going to be minus 4 sine t dt, right? Because the derivative of cosine is minus sine, okay? Now, so your dx is that then, so that's going to have a minus here, 4 sine t dt, okay? Well, that's looking a lot like we've got a minus 16, the integral from 0 to pi of sine squared t dt. Y'all buy that? Okay. Now, anyone remember how to do the integral of sine squared? Look it up in a table. It sounds like a capital way to do it. Actually, you could use your half angle formulas, but that's what the table is going to do for you too. So sine squared, in the back of your book, it's not in basic forms. It's not exponential trig. There's trig forms. There it is. Number 34. What you have? Okay. The integral of sine squared would be 1/2 of u. Well, u here is just your t. Minus 1/4 sine of 2t. Okay. We don't need the plus c. Why? Because we got things, so we're going to evaluate this from 0 to pi. So that's a minus 16. Well, let's see. Before we do that, I just hate doing too much work. Okay? Let's erase that for just a moment here. All right, we'll put some of that back. get my pen back here.